Hello, this is Vivek Rudrappa, your tech expert friend. Just imagine a supercomputer that can solve in seconds what would take today's the fastest computer thousands of years. Sounds like science fiction, right? Well, it's not. The imaginable supercomputer is now called quantum computing. In today's video, we will break down what is quantum computing, why does it matter, how is it different from classical computing, how does it work, what are real-world challenges and applications on it. Stay tuned till the end. I will show you a visual representation of how quantum computing works in real-world example. Quantum computing is a revolutionary type of computing that leverages the law of quantum mechanics to perform calculations at a speeds unimaginable by traditional computers. Let's compare what's the difference between classical versus quantum computing so that we understand it better. Data processing. Classical computing uses 0 or 1 as bits for storage, whereas quantum computing uses qubits. It can have 0, 1 or both at once. It can fluctuate between 0 to 1 in multiple ways. Processing speed. Classical computing is sequential and slower, whereas quantum computing is exponentially faster. Parallelism. Classical computing is limited to perform any parallel activities, whereas quantum computing is a massive parallelism achieved by superpositioning. Error handling in classical computing is a very less complex to handle the errors because the bits are either 0 or 1. It doesn't fluctuate. Whereas in quantum computing it's more complex due to quantum decoherence. Let's understand this with the diagram. Classical bit, it can be either 0 or 1 as a state, and all the process happens one state at a time, and the output appears in a classical computer. Whereas qubit, it can be 0, 1 or both at the same time. It can fluctuate anywhere between 0 and 1, and the state, which is called superposition state, it can process multiple states simultaneously, and the computing power happens in the quantum computer, and the result can be all collapsed to a sequential classical bit, which is 0 or 1. Let's take this analogy. Think of classical bit as a regular coin that is either heads or tails, which is 0 or 1. A qubit, however, is like a spinning coin. Until you measure it, it exists in a superposition of both heads and tails at the same time. Solving complex problems faster. IBM's quantum computers are already solving molecular simulations that take classical supercomputers millions of years. Google's Sycamore processor achieved quantum supremacy, solving a problem in 200 seconds that would take a classical computer 10,000 years. Just imagine that. Revolutionizing industries. Pharmaceutical quantum computing is accelerating drug discovery by simulating molecular interactions. Cybersecurity, quantum encryption, quantum key distribution, which is other way, will make hacking almost impossible. Finance, used for portfolio optimization, risk analysis, and fraud detection. Think about this climate, how this computing can model climate patterns and create more efficient AI models for decision making. Let's take this analogy now. Imagine trying to find a needle in a haystack. A classical computer checks each straw by straw, while a quantum computer analyzes all possible positions at once, making it millions times faster. Quantum computing relies on three key principles of quantum mechanics. One being superposition. Quantum bits, which is qubits, can be 0, 1, or both at once. Whereas this classical bit, as explained, it can be either 0 or 1, right? Let's take this analogy. Imagine a traditional computer as a single track road where cars, which is data, must travel one after another. Quantum computing, on the other hand, is like a multi-dimensional highway where cars can take multiple paths simultaneously. Second one being entanglement. Qubits stay connected no matter the distance. Two qubits can be entangled, meaning a change in one qubit instantly affects the other, even if they are light years apart. Let's take this analogy. Imagine having two magic dice. No matter how far apart they are, if you roll one and get a 6, the other will also land on a 6 instantly. The third and final principle of quantum mechanics is quantum interference, enhancing probability of right answer. Quantum interference helps steer quantum computations toward the correct answer by amplifying right probabilities and cancelling out incorrect ones. Let's take this analogy of a water wave. It's like adjusting the waves in a pond so that only the biggest and most useful ones remain. Quantum computing also comes its own challenges, and there are solutions to come over it. First challenge being quantum decoherence, which is loss of quantum state. Solution could be cryogenic cooling and quantum error corrections. Second challenge is scalability. Developing more stable qubits using superconductors and topological qubits could be the solution. The third challenge is hardware limitations. Solutions: companies like IBM, Google, D-Wave are investing billions to improve quantum hardware. Why do you think quantum computing is the future? Quantum computing isn't just an upgrade, it's a revolution. It can solve problems classical computers never could have. It will transform industries from AI to cryptography. While challenges remain, big tech companies are rapidly advancing quantum technology. What do you think? Will quantum computing change the world? Will quantum computing take over the classical computing, or both coexist? Drop your thoughts in the comments.